All right. Yeah. So hi everyone. Thanks for being here today. So today we start our new year with a new seminar with the IFI, and today we have Sam Bright-Thonney. Is one of the new fellows that just started last year in September. So Sam completed his PhD in Cornell in 2024, and now is since last September is a IFI fellow here. So we are all eager to hear about his current research and previous research that is going to talk about today. So I'm happy to leave you the floor.
Is this working? Okay, great. Um, all right, yeah. So hi everybody. I'm Sam. I think I've met most of you now at some point or other, but it's good to, I guess, formally stand in front of you and tell you what I work on. So today I'm going to tell you about some of the work that I've done previously and a little bit of the work that I'm doing now, unified by the theme of sort of compressing collider data into embedding spaces that we can use for a myriad of interesting downstream tasks. Um, so I'll start off the talk, not on colliders, but on foundation models. And I promise this is not going to be a foundation model talk. I think it's just it's a useful way to frame what I'll discuss. But I think, it's kind of undeniable that the modern AI landscape is, to a large extent, the landscape of foundation models. And, what one means by a foundation model, if you go by the definition that the Stanford group decided in 2021, it's any model that's trained on a broad data that can be adapted to a wide range of downstream tasks. And the ones that really everybody knows about now are these language foundation models. So ChatGPT or Claude or now DeepSeek. They're trained on the entire internet and all of your text messages and all of the textbooks you've ever read. And they have these emergent capabilities to do all kinds of things that we care about, like write code, write essays. Um, and yeah, this kind of language is mastering language. I would say is the most viscerally impressive task to come out of AI in the last 10 to 20 years. But I think LLMs really dominate the conversation, at least like on the news. Um, and there's a strong argument that you can make that if I consider an LLM as just a model that understands language, then if I substitute X for language, where X is any scientific domain, then a foundation model for a scientific domain can be extremely, extremely valuable. And if you need evidence of this, two people just last year won the chemistry Nobel Prize for writing a machine learning model that can do protein folding. And whether or not this thing, I think AlphaFold is not typically discussed as a foundation model, but it's something that understands protein. So there, in some kind of approximation, you could call this a foundation model. And more recently, or concurrently, I guess, with AlphaFold, you're seeing these huge, large-scale models being trained on across a wide variety of scientific domains. I think one of the most exciting sort of avenues right now is materials discovery. So using diffusion models to maybe find room temperature superconductors, or to find the next cancer drug, or a myriad of really useful things you could do with this. But I'm a particle physicist. I'm not a chemist. I'm not a biologist. So naturally, I would want a foundation model that understands particle physics. Um, so I can go to ChatGPT and I can ask it to give me a concise technical explanation of asymptotic freedom in QCD. And it'll give me something that is really, really accurate, and it seems to know what it's talking about. So I guess we're done. We've got a foundation model that understands physics, so we can all go home. That's of course not actually what I mean. What I mean when I say a foundation model that understands physics is one that understands physics data. And in the particle physics world, physics data comes in many, many shapes and forms. And depending on the experiment that you're working on, the detector technology that you're using, the energy scale of your collider, your data can look very, very different. Um, so what I kind of more specifically mean here is, let me choose an experiment. So I work on CMS. So I want a foundation model maybe that understands CMS data. And I train some huge neural network, a transformer or something, in a self-supervised way. And I trust that if I train it on enough data for long enough with enough GPUs, then it will understand particle physics. And then I can use this thing for a bunch of downstream tasks that I care about as a particle physicist. So measuring properties of the standard model, like the Higgs boson, tagging interesting objects, doing anomaly detection to look for evidence of new phenomena. There's a whole bunch of things that a big, capable ChatGPT-like model could do for you in particle physics. Um, so I can ask a little bit more of a, a little bit better in light of the way that our data looks. We can ask a more detailed question of LLM. So if they can code and write, and can they also do my job in their current form? So I can take this picture of a Higgs to gamma gamma event from CMS, and I can ask ChatGPT, what's going on here, and it kind of gives me this long filibustery answer about like, oh, I think that's the CMS detector, and here's a bunch of things that could be going on. And it gets a few things right. So it's like it knows that this is CMS. It kind of guesses that it might be a Higgs event, but that's probably just because most people are writing about the Higgs on the internet. But it gets a bunch of stupid things wrong. So it calls photons missing energy. It doesn't know what any of the calorimeters are. Obviously, it doesn't quite know what it's looking at. And then, if I, let's say this wasn't a labeled event and I wanted to know what was going on, you can ask it, to tell you what's going on, and then it completely filibusters again. It gives you like paragraphs and paragraphs of essentially guesses about what could be going on. So it's pretty clear, that LLMs, they can do a lot of things, but they can't do particle physics yet. So this kind of begs the question now, what do I really specifically mean by a foundation model? And to begin answering this question, it's useful to think about like the sort of many, many ways in which particle physics data is very different from language. So first of, I guess, foremost, is that it's very, very high dimensional, and it's not like naturally tokenized the way language is. So we have, like hundreds and hundreds of particles in every collision, and their energies and momenta are all continuous quantities, and there's no, natural way to order them. So you could train an LLM style model to take in particle physics data, but you'll be imposing kind of an unnatural order on what's going on here. And then, secondly, the interpretation of any kind of particle physics, data is statistical. So I can't just like take this picture and then say that I've discovered something because I think I know what's going on in this picture. I have to, collect millions and millions of events and gradually find something like the Higgs boson. And then it also, the data is inherently context dependent. So this is one experiment, and there are many experiments that I could build and think about. And the last one, which is more relevant for, I guess, kind of granular, implementation of models, is that you kind of have to decide at what scale you're talking about the data. So, if I gave you every readout channel from the CMS detector, you can't, like, there's no model in the world that could handle this because it's millions and millions of channels. And then so even if I'm, talking about like an electron, I can either give you a 4 vector that I've reconstructed from all of my detector elements, or I could give you like 10,000 calorimeter cells and like the energy in those calorimeter cells. And it's not like immediately obvious, which one of these is the best one to use for any given problem. And then the last one, which I think is maybe the biggest difference between like scientists' goals and OpenAI's goals, is that like in particle physics, by and large, from my perspective, this might be controversial. We really don't care so much about generative models. So like the selling point of ChatGPT is that it can write you an essay, and I don't really want a model that can write, construct particle physics events. I have a collider and I have a detector to do that. So the foundation model should really be doing something else. So the kind of the view that I'm going to advertise in this talk, and this is where I'm going to stop saying the words foundation model for the most part, is this view of taking this really messy, noisy, high-dimensional data from our particle colliders, using some kind of thing that it's really just convenient to call a foundation model. But what I just mean is a large model that can obtain many myriad capabilities through training on large amounts of data, and then construct some kind of low-dimensional, hopefully physically meaningful embedding space for this data. And so you can imagine, conceptually, I take the ensemble of collider physics events, I put them through this machine, and then each event gets mapped to some point in this space. And if you train it in a clever way, then perhaps this space has structure. So, Higgs physics, like boosted Higgs bosons, maybe live in one corner. Maybe electroweak style stuff lives in another corner, and then maybe the new physics that I want to find lives somewhere else. And kind of the name of the game here is building this model, and there's a lot of fun kind of inductive biases and model design that goes into thinking about these problems. Right. So just an outline for what I'll talk about the rest of the the hour. So I'll start with an LHC physics primer, just in case people have different backgrounds. Just a few things that you need to know to understand the later parts of the talk. And then I'll talk about progress that we've been making over the last couple of years towards this building these useful spaces for embedding collider physics events. So the first product I'll talk about is what we call a semi-supervised approach to constructing this space. and we use it to do anomaly detection. So looking for some heavy new particle that gets produced in collisions and then decays to something. And we're pretty agnostic about what it decays to. And then the second project that I'll talk about is, kind of the more general version of the semi-supervised space is a self-supervised space. So this is really more along the lines of, what a modern foundation model would do. So you give the model a bunch of training data, and you define an objective that doesn't require labels necessarily, and then you tell it to construct its own embedding space just by looking at the structure of the data. And then we use this to also do anomaly detection. And then if I have time at the end, I'll talk a little bit about some work that we've done towards correcting biases in the simulation data that we use to train these models. And then I'll end just with a little bit of a couple words about the future and where this work is going. Okay, so just getting started. In case you weren't aware, I think we have a lot of LHC talks in this building, but the LHC, the Large Hadron Collider, is a big proton-proton machine in outside Geneva, Switzerland. It's the world's largest collider, and at the LHC we collide bunches of protons at an enormous energy, and we use what comes out of these collisions to learn about the fundamental forces of the universe. And if you go to Geneva, you can drive around the ring and you can visit all of these experiments that we've built to look at what goes on in these collisions. The one I work on is called CMS, or the compact muon solenoid. And it's this huge behemoth of a machine. But essentially, what it's designed to do is take photographs of, quote unquote, photographs of what's happening when I collide bunches of protons together. So the beams come together in the middle here, and then the particles that get produced, they pass through many, many layers of detecting material, and what you get out at the end is a picture that looks like this. And using, complicated software, we can reconstruct trajectories, we can reconstruct energies, and we can kind of put labels on what we observe. So the things we care about, though, are quite a lot different, at least on paper, than the things that we can measure. So what we measure is some messy, bag of like 200 to 1,000 particles come flying out of a collision. What we actually care about is kind of at the Feynman diagram level. So somewhere deep inside this, bunch of protons that's colliding, maybe, a Higgs, two quarks are interacting and producing a Higgs boson, and then we observe what the Higgs decays to. And really what we want to learn is something about this coupling here. So this mismatch between sort of the messiness of the things we measure and the cleanness of the things that we care about makes this, LHC physics really well suited for AI. Because AI tools are really built for handling complex and high-dimensional data. And so the workflow, at the LHC, it starts by, you make your collisions, but the collisions happen at a rate that is far, far too large to save, everything that happens to disk. So the first thing that you do is you put all of your data through a trigger, which is essentially a really, really, really quick decision that usually is made at the hardware level about whether or not I want to keep an event. And until very recently, AI wasn't really a thing at the trigger level because it's very, very hard to make, large, heavyweight machine learning algorithms operate on like a microsecond timescale. But in the upcoming upgrade and run 3 of the LHC a few years from now, there's a lot of work that's going on, especially here at MIT, to deploy AI on FPGAs and actually run it in real time and put it in the trigger. And this is hopefully something that I'll be working on during my time here in the next few years. But this talk is really going to focus on the last stage of the physics pipeline, which is analyzing the data. And this is a very, very busy field in the world of AI. There you can visit the High Energy Physics Machine Learning Living Review to look at all the papers and all the methods that people are proposing to use AI to accelerate this process. And you could spend probably the rest of your career just reading those papers. And then, okay, so this is a little bit discontinuous here, but there is one very specific physicsy thing that I need to talk about in order for you to understand the next part of the talk, which is jets. So it's often the case that the things that we care about observing in a particle collision at the Feynman diagram level are like the quarks and gluons that are produced during a collision. So for example, a top quark. We care about measuring things about top quarks, but because of a phenomenon called color confinement in QCD, we can never actually measure a top quark in the detector. You produce a quark in the collision, and then very, very quickly it fragments into a bunch of other QCD particles. And then before, like long, long, long before it ever reaches the detector, it has hadronized into like 10 to 100 stable particles that we can measure. Then so what we actually see in the detector is not a quark, not like one particle, not the top quark, but some kind of collimated stream of particles that are all going in the same direction, and from which we have to infer what went on. And this is what we call a jet. And one of the interesting things about jets is that if they come from a boosted particle, so let's say a Z boson that decays to two quarks, if it's at rest, then I would get two jets. But often what we care about is particles like Z's or Higgs with large boosts. And what tends to happen is that our reconstruction algorithms, our clustering algorithms that we use to make the jets, will capture both of those quarks decay products in the jet. And this is what we would call a two-prong jet. And often the substructure of a jet, so the number of prongs, is something that we care a lot about, and it can tell us about the physics process that produced the jet. All right, so hopefully that was enough explanation of LHC physics to make the rest of the talk make a little bit of sense. So the first project I'll talk about is these semi-supervised spaces that I mentioned at the beginning, and this is essentially trying to construct one of those cartoon spaces that I drew earlier, using machine learning, but doing it in a much more sort of by hand way, which I'll get into. And the problem that we're applying this to is the problem of anomaly detection. So looking for something in the data that is not the standard model, but we aren't being specific about what that is. And just to motivate, like why we want to do that. A lot of people in the room are particle physicists, so you'll know that we've been doing LHC physics now for 15 years, and the standard model has withstood frustratingly every single test that we've thrown at it. And so there's kind of no longer an obvious experimental target for looking for new physics. We used to think that it was probably SUSY, and we spent a long time looking for SUSY, and we didn't find SUSY. Now we don't really know where to look. So if you think of theory space, like all the things that Jesse could write down that could be new physics, there is like orders and orders of magnitudes, more theories that I could test than we have time in the universe or grad students available to do. So ideally, if I'm doing a search at CMS, I want to look for as many as I can. I want to exclude as many new possibilities as I can at a time. And this is what people typically refer to as a model agnostic search. So I'm searching for something, but that's as specific as I'm going to get about what I'm searching for. And okay, nominally this has nothing to do with embedding spaces, but you can think about why constructing an embedding with a big model might help for this task. And the first reason is that anomaly detection in like a really, really high dimensional data set, let's say like a 10,000 dimensional data set that I construct from every particle in a collision in CMS, doing anomaly detection there is very, very hard. It's like inherently an extremely sparse problem. It's difficult to model. There's tons and tons of tails, and it becomes difficult to even define what you mean by an anomaly, and certainly to make any statistical statements about one. A second motivation is to perhaps alleviate some of the trade-off that we typically see in particle physics between like the granularity of the inputs that you use for your problem and the performance of your algorithm. So one way to do an anomaly search is to take one observable and look for, model the background processes in that observable, and then look for some deviation in the distribution of that thing. But in that case, you're only looking at one observable, and it's possible that an anomaly in your data set is in some other observable. And by, allowing the machine learning algorithm to construct this space, then maybe you can, you feed it all of the information, and then it gives you a small amount of information, and maybe it's, compressed this high dimensional information in a way that is more useful than what I could come up with for doing anomaly. And then the last point, which is more dependent on your sort of compression algorithm, I guess, is the interpretation of an anomaly might be easier. So if this, if I kind of know how the standard model populates this space, if I see some kind of cluster of anomalous events, then maybe something about where they are in the space can tell me about the underlying physics. So if I want to go about designing model agnostic search, I have to decide, at least on some level what I'm looking for. So usually in particle physics, this is a new particle, which can be anything. And then I have to decide, what signature am I going to look for in the detector. And the most simple thing you can look for in any experiment, any symmetric beam experiment is, a two-body decay. So some particle that gets produced and then decays into two things. And then I measure the two things, and I infer that the particle was there. And for this project, we're assuming that these decays are hadronic. So this is a pair of jets, maybe back to back, whose invariant mass, if I measure their four vectors, is exactly equal or close to the mass of this new particle. And we call this thing a dijet resonance. And if I take all the events at CMS that have a pair of jets in them, I construct this invariant mass and I make a histogram of it. A resonance looks like a bump on this histogram. So we're just looking for a bump in the dijet mass spectrum. And it sounds pretty straightforward, right? But the problem is, the standard model strikes back. If you just take all the dijet events at CMS and you put them in a histogram, you're going to have like billions and billions and billions of really, really boring QCD, and you have no hope of finding a signal unless it was like the dominant process occurring, which it, of course, isn't, because we would have found it already. Okay, I skipped ahead a little bit. But like, so to zeroth order, the simplest thing that you might want to do to look for an anomaly in the dijet mass spectrum is to take a bunch of auxiliary observables, so other things that you measure from the event, and train some kind of, let's say, density estimator or something on standard model backgrounds. And then if I take the score for every event, I put it through my model and I compute the log likelihood of that event, and I put those scores on a one-dimensional axis, then background-like stuff will be very background-like. It'll be like the thing you trained on, and non-background-like stuff will be have a higher loss. And I can, conceptually, this is a very easy thing to do. But of course, when you do this with real data, it's not quite so simple. Because the tails of the real data distribution, you don't really know what's in there. You train on simulation, you know what that is, but when you actually evaluate it, this tail could be populated by just events that were reconstructed poorly by your detector, or just, rare standard model events, like top quark or Higgs events, or, just the signal could be there, but it's very ambiguous when it's a one-dimensional problem. And so what we do here is this, I don't know if this is a standard term in the literature, but the semi-supervised approach, where instead of just having one axis that parameterizes that measures how sort of standard model-like an event is, you add another axis, you choose some kind of representative signal of the kind of new physics you might be looking for, and then you make another axis that measures how signal-like the event. And then this pushes the distributions of things into more dimensions. Here I'm just showing two, but in general, you would have more. And so now, standard model backgrounds live kind of in this corner. The signal that you trained on maybe lives in this corner. And then like realistic DSM signals live in some, maybe roughly spread out region between them. And then things that are sort of more or maybe less interesting to you, like glitches, they don't look like anything that you would have trained on. So they live in some far corner of this space that you can easily ignore. And then to do a search for new physics, I just look in this region that is kind of away from where I know the background should be. And this approach has a name. It's called the quasi-anomalous knowledge technique, or QUAC. And it was developed in Phil's lab a couple of years ago, and we've now demonstrated it for the first time on real data from CMS. Let's see, how am I doing? Okay, so the name of the game here then is choosing. I know that one of these axes should be a background-like axis. So what I have to do is then choose a few what we call physics priors or signal priors for what like a new dijet resonance might look like if it came from a new physics process. And I want to be pretty agnostic about like what this is a two-body decay of some new particle A, and I want to be pretty agnostic about what B and C are. And all I'm assuming is that they're light enough relative to A that all of their decay products are captured in one jet. And so this jet could have interesting substructure. And so the way that we break down the problem is to parameterize the new physics signals according to like what these two decay processes look like. So you could have two one-prong decays, you could have a 3 and a 3, or a 2 and a 5. And this is just a way to sort of write down all the hypotheses that you might have. And then we go to the big bank of like CMS internal Monte Carlo simulation that we have. We find every possible signal that we could train on that has a range of masses and a range of substructures, and we construct our space from these events. A little bit of specifics. The density estimator that we use is a normalizing flow trained on about 14 inputs from the event, so 7 from each jet. And constructing the space is essentially you train the flow, and then for to locate in a given event in the space, you evaluate the log likelihood under that flow, and you keep doing this for the background-like axis, and then for each signal-like axis, and you keep going with as many axes as you want. And then to make the problem a little bit easier on in terms of like actually doing the analysis, we devised a technique to reduce all of these signal-like directions just to one these kind of summary direction. And that what we end up with is a space that looks like this. And you can ask me offline about why it looks like this. There's a reason for the existence of these two lobes. But the short story here is that if these blue blobs are the Monte Carlo, the background Monte Carlo that was trained on, so it's like this horizontal axis here, and then these colored blobs are candidate signals that we injected. So like just some random choice of a new physics signal that decays to a dijet resonance, and then you kind of measure its distribution in this space, and you can see that that it lives fairly nicely separated from the background. So the space is kind of doing what we want it to do, at least for a broad class of new physics signals that we might be able to look for. And then to actually do the bump hunt, to look for a resonance, what we do is we take this space, we do a little bit of extra pre-processing on it, and then we have to devise like an unbiased procedure to look for a resonance. So let's say I'm looking for some bump in this spectrum hidden under a bunch of background at 3 TeV. So for each possible mass that this resonance could have, the procedure changes a little bit, but let's say it's 3 TeV. I draw a band in the dijet mass spectrum around 3 TeV, and I ignore that. I call that my signal region, and I ignore all the events in there for now. And then I take all the events from what's called the sideband. So dijet masses that are a little further away from the resonance mass. And then I populate the space with those events. And then the assumption here is that there might be a resonance at 3 TeV. So the events that populate this space should be essentially background-like. And then, so I populate my space with quote-unquote background-like events. I draw a contour that kind of singles out the events that are in the sparsest populated regions of this space. And then I use that contour to select events from the signal region and populate a mass spectrum. And then, if there's really signal in this signal region, then it would manifest itself as a bump, and I can just do a simple, standard LHC LHC physics style fit on the spectrum to figure out if I have any new physics. So you can go, it's a lot. It took a couple years to develop this on real data, but you can go to the real CMS data set. You can do this procedure for a bunch of hypothesis masses between 2 and 6 TeV, and then you come out with this plot. So this plot is as a function of the mass the new particle might have, basically the p-value for whether or not there's a resonance there. There's like actually a bump in the mass spectrum that you measure. So pretty clear that we haven't found new physics, at least with this analysis. Anything below 3 sigma doesn't really raise eyebrows in the particle physics community, especially considering that these are local significances. So yeah, this is no new physics yet, but you might ask the question, like, okay, you didn't find any resonances in this range. Like, was your method just not very sensitive? Like, maybe it just the thing that you designed didn't work very well. And we can actually test this. So we can inject actual signals into our data sets. We take real data and we inject some amount of some random new physics process that we choose, and then we see how sensitive would our method be if that signal were really in the data. And what we find, for every signal is kind of different. We're differently sensitive to every different new physics signal that you could write down. For this one, for example, this 2+2 prong signal, we hit a 5 sigma significance by like 10 to 15 femtobarns of injection. So this is, for reference, that's a very, very small amount of signal. So if there were something like this in the data set, we certainly would have seen it with, if it had a high enough cross section, we certainly would have seen it. And then, as I said, different physics processes we're differently sensitive to. I guess I should have noted that it's the orange line is the one that you should be focused on, which is our technique. But the story is, we are actually indeed quite sensitive to a wide range of new physics signals. And then this plot I'm showing, not because you should attempt to read it, certainly don't attempt to read this plot, but what you can go and do with this method that we've developed is you can basically test as many signals as you want. So if I have simulation, if I have Monte Carlo for a given new physics signal, I can look for it using this technique, and then I can set an upper limit on how, what the cross section for that process would be. So like how, if it really did exist, how often could it possibly be produced? So I can exclude, or I can set limits on a ton of signals at the same time, just with doing one analysis instead of 50 analysis. So yeah, that concludes that section of the talk. I don't know, are we doing questions at the end? But okay. Okay. Right, and then so the second half of the talk, there was kind of a lot of in the semi-supervised search that I just described, there's a lot that goes into designing the space. So you have to make all these decisions about what your signal prior should be. You have to devise all these techniques for selecting events in the space. This next part is just deciding to let the AI algorithm do that, using a self-supervised algorithm to construct my embedding space. Right. So the quack style of search, as I said, you do have to choose all these axes, and the space is more interpretable, so I know what each direction corresponds to in terms of background or signal. But it might not be optimal. Maybe if I let a big foundation model, a big self-supervised model learn this space, then the new physics would be like way more separated from the standard model. But with the downside is that I can't actually interpret. But maybe maybe it's easier to discover in using such an embedding. So that begs the question, like, because the space is no longer interpretable, I can't just say, okay, we're going to look in the region that is like very unbackground-like and very signal-like. I can't make like I can't make a cut by hand in the space. So how do you do the anomaly detection? How do I select events to put in my digit mass spectrum? And for this, we use this statistical method called, I think it stands for New Physics Learning Machine, but we all just call it NPLM, which you can ask Gaia all about. I think she probably talked about it in her version of this talk last year. But essentially, the idea is that you have a large sample of what the standard model background should look like, and then you have your real data. And by training a neural network or by fitting kernels with a very clever loss function, you can actually learn, essentially the likelihood ratio between your data and what the background should look like. And you can construct these test statistics that allow you to make actual like precise statistical statements about like how different your data is from the standard model. And so this is what we opt to use for these more self-supervised spaces. And then actually to construct the space, we use contrastive learning. And the way contrastive learning is really pretty simple. You have your inputs. Here, these are cats. And you do sort of random augmentations on your inputs. So if these were images, I would want my machine learning model not to care that the image is rotated. I just want it to care about the fact that there's a cat in this image. And so I pair up, images of a cat and rotated images of a cat, and I tell the machine learning model to treat those as the same. So embed those to the same point in some low-dimensional space. And then different cats obviously should go to different parts of the space. And then, dogs should go to different parts of the space as well. So the training objective for contrastive learning embedding is to pull together these augmented samples and then push everything else apart. And, you kind of hope that this imposes some structure on your embedding space that is desirable for whatever you want to do downstream. I guess the main difference between what we're doing and what computer vision people do is that it's not always obvious how you should augment your data. So for an image of a cat, I can just rotate it, I can change the colors, I can crop it. But for a physics event or for like a jet, it's not clear, what augmentation would be best or what augmentation would guide you or your machine learning model towards like learning the most optimal embedding. So what we actually do is a variant of self-supervised learning called supervised sim-clear. So instead of like taking a picture of a dog and rotating it and telling the model to put those in the same spot, we take, for example, a Higgs boson event, and then we take another Higgs boson event from the same data set, and we have it push those two together versus like a Higgs boson event and a Z boson event, we have it push those apart. And because we have, an abundance of labeled, events from simulation, this is something that is easy to do. So we can't train on real data, but it does, make the, the kind of difficult question of choosing augmentations. It does kind of alleviate that problem. And very specifically, what we do for this project that I'm going to talk about is we train on this huge data set of simulated jets. So the four classes that we consider for our training are Z boson, W boson, QCD, which is just quarks and gluons, and top quark jets. And we train them in this supervised contrastive way using a big transformer model that I won't discuss the architecture of. And what we get out at the end is actually really a quite nice looking space. So this is a 2D T-SNE embedding of what is actually secretly an 8-dimensional space. And we see that the classes that we trained on are actually quite well separated in this space. So QCD stuff lives up in this corner, top jets live down in this corner, and then WZ, they kind of overlap a little bit. They're both two-pronged, but they live over here. And they're all the three classes or the four classes that we trained on are actually pretty nicely separated, and we didn't really have to do anything other than like tell the embedder that like two events are from the same process. But the more exciting thing is that if I inject some jets that it hasn't seen in training, so like a Higgs boson, a boosted Higgs boson decaying into two B quarks, it puts it in kind of a reasonable part of the space that is like distinct from the other. It doesn't have exactly the same distribution as one of the other classes. So it's actually, when you give it unseen data, it does something with it that is different than what it's doing with the other stuff. And this means that maybe, if the Higgs boson were in my data set, I would be able to find it by looking at this space. And that's exactly what we do. So this kind of demonstration that we've done recently was the task was not finding new physics, just simply finding the Higgs in a reference data set that's made of the most common background, so QCD, WZ, and top. And what we do is we just inject increasing numbers of Higgs jets into a large data set of backgrounds. And we do this NPLM statistical test on these injections. And we found that, this is just a random example that I've chosen here, but like injecting 500 Higgs jets into a data set of, 250,000, you can find, a discrepancy at like a 6 sigma level, 7 sigma level. So it's very, very sensitive to, really small signal to noise ratios. And then you can repeat this with a bunch of different injection levels and with a bunch of different model architectures. So this is varying the different colors here are varying the dimensionality of the space. And you find that, kind of across the board, by the time you're injecting like 300 signal events, Higgs events, you're hitting, a 5 sigma threshold, which is like the industry standard for, discovery. And then if you, this is, I guess I should note that this is on a pretty small sample of events. This is 250,000 events, which by LHC standards is a really small data set. So if you kind of scale this up to like the actual luminosity of like of the CMS run 2 data set, then we would expect to see, for example, the Higgs at 4 sigma at like a 0.005% signal contamination, which, to compare to the actual dedicated CMS search for H2BB bar, this is about the same, signal to background ratio that they were working with to make a 4 sigma observation. Except here we haven't, designed an analysis. We haven't, this was very specifically looking for Higgs to BB bar. This was just training on some backgrounds and then doing a statistical test on the learned embedding space. And I have to put a caveat here. These two setups are like meaningfully different in a lot of ways, but we're working on kind of demonstrating this in a more realistic LHC analysis style data set, and hopefully we'll have results for that soon. But as a back of the envelope estimate for how sensitive using a contrastive embedding could be for discovering things, or for even just measuring things are there, like the Higgs, this is like a very promising sign. Okay, perfect. I think I only have 10 more minutes, so I'll wrap up. Okay, I do have time to talk about this, so I will. So the last thing that I want to talk about is robustness. So basically everything that I've described to you so far, the machine learning models that we train are trained on simulation. And simulation is wrong in ways that we understand. It's also wrong in ways that we don't understand so well. And it would, you can kind of ask the question that, like, okay, if you're training a foundation model on simulated data, what could go wrong if there's like if the simulation you're training on is just not quite accurately representing reality? And all of the wrongness in your simulated data will need to be accounted for downstream when you actually make a measurement. And kind of, let's say that this is the blue is my distribution of background of simulation, and the green is my distribution of real data, background only real data. One thing that you can do, which is like a very popular technique, is just reweighting the simulation. So I train a classifier on signal on data versus simulation, and then I learn a weight, and I can reweight my simulation to look just like data. And this works for most of the time, but it can't really account for like discrepancies in the tail. There's no simulation events in this tail, so there's nothing to reweight to look more like data in that tail. So like you have to come up with maybe a different or cleverer way to account for discrepancy. And to, I guess, put a concrete spin on this, we can take a benchmark data set that was used for an anomaly detection challenge in the high energy physics community called the LHC Olympics data set. We can train a contrastive space on it using all of the particle level inputs. And you don't the green blob in this picture is not so important. The two important things to look at are the purple blob and the red blob. So in this LHC Olympics setup, the purple blob was the simulated data that they gave you for training. And then the red blob was like the actual data that they injected the signal into for the anomaly detection challenge. So this is kind of mimicking like a distributional difference between the data, the simulated background that you train on, and the true background in like the real data set. And so what we did is we developed this technique called chain quantile morphing, which uses normalizing flows to basically correct the background in a way that accounts for discrepancies in the tail. And you can get the like the real background and the simulated background to actually look the same with this technique. And then you can train downstream classifiers. So this is a very, very simple case where I just have some random signal that I'm looking for, and I train a classifier to look for it using this embedding. And I guess there's two stories here. One of them is that like the blue curve here agrees really well with the green curve, which means that this morphing technique for correcting simulation discrepancies worked really well. And the second story here is actually like a second order story about why contrastive spaces are nice. Because if I train a tagger, for a signal versus background tagger from scratch on like all the particles in a jet, I get the performance, this nice performance that you see in this top row of the table. But I can also just like train this contrastive embedding and then train like a tiny MLP to do signal versus background classification in this space, and it basically achieves exactly the same performance. So it's not really the story. The story here is that you can correct simulated data to look more like real data, but the second story here is that these contrastive spaces are actually quite useful for downstream tasks. And with that, I think I'm just about out of time. Actually, not quite, but so I'll just briefly talk about some things that we have in the pipeline for the next couple of years and where I think some of this work is going. So yeah, the vision that I think I've tried to lay out here is what I'm calling one space to rule them all. So like the long future of what this might be is I have some kind of physics foundation model that I train on collider data. And then from this embedding space that I get from it, I can do, like any analysis that I want. I can do a Higgs search, I can do an anomaly search, I can do some other kind of standard model measurement, really whatever you want. And like this sort of universal pre-processing layer simplifies all of these downstream tasks and sort of makes the timeline for doing them a lot faster. And just in terms of some things that I'm working on right now that you can ask me about after the talk. One of them is developing this contrastive space that I just described to you into like a full scale demonstration on a more realistic LHC style data set, so we can actually do an apples to apples comparison with that Higgs measurement. The second one is, I think I alluded to near the beginning of the talk, is thinking about what a foundation model might be useful for at the trigger level. So if you can imagine, I have a real if I have a low dimensional embedding that I know what standard model looks like at the trigger level, then I could pretty efficiently trigger on stuff that I know doesn't look like the standard model. So you could design anomaly triggers this way, and this is already being done in kind of slightly different contexts. And then the last thing is, Phil's very involved in LIGO, so I've been thinking about, taking some of these techniques and building contrastive spaces to do, anomaly detection searches with the LIGO data, which is a very different setting, but, the technique is hopefully generalizable across domains. And yeah, I think I've already basically said this slide, but like the idea here is just kind of a new workflow for doing high energy physics. The model for the last 50 years has been like you choose something you want to do, and then you spend like 3 or 4 years or 10 years, if in the case of like the W mass measurement, designing a really, really careful way to do it. And this involves like constructing a bunch of hand-tuned observables and calibrating, and all these things are important, but the hope is that like you can speed up whatever you want to do by having some kind of foundation model that takes all the information in an event, compresses it to a low dimensional space while preserving the information that's relevant, and then allows you to do what you care about easier and faster. And kind of, I think the most fun and promising direction for the next few years is figuring out how to do this in a way that is scalable and which is kind of reliable when you're actually deploying it on real data. So yeah, I'll leave with this slide, because I realized that last semester I was on a plane when this like IAIFI event happened where everybody did one slide about themselves, and I didn't get to present this. So these are things that you can ask me about offline. But thanks for listening, and yeah, I'll take questions.
All right. Thanks, Sam. Are there questions in the room?
Thanks, Sam. Really great to hear about this. So I'm curious about the bulldozer. And so in a previous era, CMS had this music program of kind of modeled unspecified searches where you make a bunch of little boxes looking for anomalies and you try to characterize the background and all those boxes. And I'm curious if you can talk about how that approach of trying to search a large space differs from this kind of learned embedding, and what were challenges of kind of old style try to search everywhere versus what are the benefits of the type of thing that you're doing now?
So are you referring to a specific effort?
Yeah, so
the music?
The music effort.
Okay, so I'm not deeply familiar with that or how it works. But I would say that I think like, from my perspective, the strength of doing something like this is that like, you have the space, and then like, let's say you want to look for like diject resonances. You can like cut away, you can still make like normal cuts, but then you can use the space itself to do your statistical test. And the idea is that like, okay, maybe I'll cut on some like high level observables that I've designed, like HT or whatever, to like isolate the events that or to throw away the events that I know I don't care about. But then like doing something like NPLM on the embedding space is the features are less interpretable, but maybe they encode something that is, more representative of the whole event than like a collection of, observables that I choose by hand. And like NPLM is also very, very sensitive and very, very powerful, even to like, very small amounts of signal. So it's really, I guess, the power of the statistical test that I think is, yeah, that's one of the main advantages. But I can't comment on exactly what music was doing because I wasn't involved in that. Yeah, yeah. So this is this is like a long time in the making, but let me get back to it. Basically, we were trying to figure out how to make the analysis more in this slide. Right. So basically trying to figure out how to make like, so in some sense, like what you're doing, if you have a bunch of signal like priors, you're replacing one high dimensional problem with another one. So like I could do like 30 signal hypotheses. That's pretty hard to like like a 30-dimensional histogram is pretty hard to like cut in, and the space is hard to think about and like reason about visually. So we designed this like, I forget what it was. It was some kind of like signed norm reduction. So you take all the signal like axes, and then like depending on the relative position along the axis, there's like a normalization step that we do to all the scores first. So basically, like a large positive score is weighted in a large positive way, and a large negative score is weighted in a large negative way. And then so like, when you reduce this y-axis to one dimension, you get these two lobes, like ones that have been negatively weighted in a large way by one or many of the axes, and then ones that have been positively weighted. And so, yeah, and the signals tend to, obviously, like the actual signals tend to be, in the more positive direction, but our template method for like selecting events from the signal region is agnostic about which exact like lobe it's in. You just kind of shift the whole thing up into the top half. Simon?
Ooh, a microphone. Yeah. On this same slide, why is there like a positive correlation between being background-like and being signal-like?
So this is, I guess, right, this is the kind of a mislabeling. So background-like means lower, so basically the left is more background-like, from what I recall. So like it's like a lower score. So like like more background-like actually. Yeah, negative likelihood.
Thank you.